recording, sharing my screen. Thank you, Dory. Okay, a note. Good thing I added it here because I almost forgot. Thursday next week, I have an appointment and I can't come to class. Okay? And so what I'll do instead is I'll post some videos for you to watch kind of on your own time whenever you want. And so just be aware that we're not going to meet next Thursday, the 13th. Okay? We've got test number 2 on November 20th, so the following Thursday. Okay, of course, I'll see you. Well, I guess I won't see you the Tuesday before this because that's Remembrance Day. I'll be out in the cold because my husband's military, so I can't skip it. And so we always call it the coldest day of the year because you have to stand outside just for hours. November 11th, the coldest day of the year. Hey, I forgot my puppy. And then things kind of got bungled, and so November 13th, then we'll be back and do some material, and we'll review the stuff in the video as well. And so test number 2 will be on chapters 3 and 4. And yeah, so not 1 and 2, of course, it's just chapters 3 and 4. And we just started chapter 4 last week, and so it's a little bit of, any questions about that before we kind of jump into it? Okay. So a little bit of review. We started exponential functions, right? And we said, okay, well, we could have, I'll do a little mini version up here, right? I could have exponential growth, or I could have decay looking like this, right? And so there's always that kind of curvature. So we're moving away from linear functions and working on these exponential functions. And what we said last day and what we worked with last day is we can have 2 forms of the same equation, right? And so generally, if you're given R, the rate of the growth or potentially the decay, then this version of the formula will be the easier way to go. Okay? If you're not given the rate, right, then usually you're either trying to figure out what this equation looks like, right, or just graphing it maybe, right, then this a times b to the x is going to be the easier version to work with. Notice that you have a in both scenarios, where a is, a is the initial or the starting value of the function, right? So where you start, and then it keeps growing. And b, of course, you could replace it with 1 plus r if you wanted to, if you needed to get back to the original equation. But it depends on what you're given. We're going to limit b to positive values, and we talked about kind of why that is, but b is going to be greater than 0. Okay, so not including 0, because 0 times anything is just going to make 0, and it doesn't, we're not interested in that. And so we limit b to be greater than 0, because negative powers of negative numbers are weird. We also introduced the continuous growth formula. So continuous growth is very similar to what we see in the exponential functions. It's just that our base, e, is Euler's number e, which is on your calculator. It's just like pi, it's an irrational number, and so just 2.71828, blah, 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 blah. Okay. And so E is roughly, I want to say, let's see here. On this one, it's in my alpha. E is roughly 2.71828, blah, blah, blah. Just as before, A is the starting amount, right? And then R is going to be the continuous growth rate. Right? And you might remember what makes an exponential function. Notice in both these cases, right, I have an x in the power, or in the exponent, right? And the x is in the exponent. And so that's what makes exponential functions. We also introduced last day, so this is from last week. We have compound interest, which is from financial math, right? So the accumulated amount in an account after some years T is going to be A, which is your starting amount, times 1 plus R, the rate of the interest rate that you got, right, as a decimal, divided by K. K is going to be the number of compoundings per year. So usually monthly or semi-annually, right? And so K over K is the number of compoundings per year. Now we had an example that I just copied from last week, and I skipped some work. This is all you need to show in terms of your work. Or sorry, I want to see the full unrounded decimal as well. But I guess I skipped that. Bad, Emily. Bad. We invested $1,000 at a rate of 1% compounded monthly for 10 years. How much are we going to have in the account after 10 years? We're going to have $1,105.12, which means that we earned $105.12 in interest. Now, to compare compounding monthly, right, with compounding continuously, this is where we left off. And I said, due for review on Tuesday. Well, here we are today. Extra big smiley face. We're going to deposit the same $1,000 in a savings account that earns 1%. So that same 1% as before, compounded continuously now. Yeah? And so find the amount in the account after 10 years. So if we have continuous growth, then we can use this formula here. F of x is A times e to the r times x. Let me just maybe bump this down. A e to the r times x. For continuously compounded questions, we could rewrite this as A of t, right? Replacing the generic F with A, which is the accumulated amount after some amount T. So all the X's are replaced with T's, and we get A times e to the power of R times T. T is in years, so that's good. And we want to find A of 10, starting at $1,000. E is just a number, right? So times e to the power of 0.01 times 10. Well, I better. Start with that power, 0.01 times 10. We have 1,000 times e to the 0.1. E to the power of 0.1, alpha e to the power of that guy, times 1,000, because it's easier to just go through the calculations, especially because I'm rounding later anyways. 1105, 170918. So the accumulated amount after 10 years is 1105, 17, which is eerily similar to compounding monthly, right? Even though we talked about compounding continuously last day, we said, okay, on a continuous scale, we're just going to check in and figure out how much interest have you earned and add that to what you initially invested. And now you're earning interest on what you initially invested, as well as the interest that you've earned. And so compounding continuously sounds great, okay? But what happens effectively is it behaves very similarly to compounding monthly. So here, notice this amount is very similar to compounding monthly. Say it above. So the difference between the two results is it exists, but it's going to be pretty minimal. Yeah? Most mortgages and I think loans in general, maybe loans, depending on what kind of loan it is, they might be monthly, right? Because they want you to pay your interest if you haven't paid up. But mortgages, I know, compound semi-annually, so twice per year, even though you make payments monthly. Okay? But this isn't a financial math course. You could take Math 114 for that. How about a bacteria population grows at a continuous rate? Now, the reason we have to pay attention is because we use a slightly different formula. So just to pick the right formula, right? Of 4% hourly. Yeah? Now, this rate is hourly, right? So we want to pay attention to that. Yeah? How much will a population of 1,000 bacteria grow to in one day? What we want to do is we want to make sure that our rate and our time frames match. So one day is 24 hours. From our continuous growth function, a e to the r times x, make that x look normal. We have that 4% hourly, but I want it to go for 24 hours. And I'm starting with 1,000 bacteria. And so I want to find F of 24 for starting at 1,000. E to the power of 0.04 times 24. Making sure you simplify the power first and then do e to the power of that and then times 1,000. No other order. 0.04 times 24 see here, e to the 0.96. Now e to the power of that guy times 1,000. 2611.696473. And you can just leave it there if you want. Obviously, you can't have 0.696 of a bacteria. And so usually we would round up, right, to the whole number. Yeah. Can't have 0.696 of a bacteria. So we usually round up. Even if the rounding, you wouldn't typically round up. Usually we do round up, but in this course, I wouldn't say that that's terribly important. Bacteria. I would be happy if you just ended here. That's what I'm going for, right? And then context will tell you, right, if it's appropriate to round or not. But that's more work experience than anything else. Right? Once you're on the job, then you'll know. Do I round this up or no? Right? Do we round down? Do you just approximate? Who cares about the formula? That kind of thing. I'll do a little check mark here that I would be happy there. Okay. Exponential functions. Good. Maybe I'll just keep it on a new page. Why not? We're going to do just a brief introduction, I would say, to the graphs of exponential functions. We've already seen that, okay, I could have exponential growth, or I could have exponential decay looking like this. I really can't remember what I was going to put here, but if R is, let's see here, if R is between 0 and 1, then we have growth. In f of x is equal to a times 1 plus r to the power of x. And if r is between -1 and 0, not including 0 because I already included 0 in the growth. But if the rate is 0, then really nothing's happening. Then we have decay. One plus r, right? That's going to take the place of our b in general, right? And so b is 1 plus r. So if r is between 0 and 1, right, then I can start at 1 plus 0 and I can move up to 1 plus 1, right? Putting b somewhere between 1 and 2, right? And so what we say is that if b is greater than 1, then it's going to be increasing. right? Just because the r is between 0 and 1, right? A positive rate. Yeah? And if r is between -1 and 0, not including 0, then we say that, okay, so r can go from -1, which puts me at a b of 0, right? 1 plus -1, up to 1 plus 0, putting me at 1. However, note b has to be greater than 0, okay? Which means that really we don't include the -1 for r. But if b is between 0 and 1, right, then you'll have a decreasing function. And if b is greater than 1, then it's going to be increasing. A is going to be the vertical intercept of the graph. Why? Since f of 0 is a times b to the 0, anything to the power of 0 is 1, right? And so that's really just a. In this graph here, right, f of 0 is 1, so a would be 1 in this case. The graph is going to have a horizontal asymptote at y equals 0. So here at y equals 0, you have this horizontal asymptote. And if you want to talk about how A influences the graph, so the graph will be concave up. Remember, concave up is this way, right? And if A is greater than 0 and concave down, well, that's when we flip it upside down, right? If A is less than 0. So same type of behavior that we're used to seeing. So concave up is going to look something like this, right? With the cup facing up versus concave down, then we have it flipped and it's facing down. The domain of exponential functions, so what values of x can I put in here, is just all real numbers, which is really any number from -infinity to +infinity. And because we have a horizontal asymptote at y equals 0, then the range of the function doesn't include 0 because it can never get to the horizontal asymptote, but it does go up to +infinity. When you're sketching an exponential function, which we're not going to do a lot of, but might be helpful to try to figure out what some reasonable answers are. So if you're sketching the graph of an exponential function, then the graph will always pass through the points 0a, like we saw, right? So when x is 0, then the output is a. Right? And also, when x is 1, it'll pass through AB. And so we saw the first one earlier. And so f of 1 is a times b to the 1, which is just AB. That's nice. Because if we can figure out, okay, when x is 0, then I know what a is. And when x is 1, I know what AB is. But if I already know what a is, then I can easily figure out what b is as well. So if we have to match the functions to each of these graphs, let's start with 0a. So all of these except for one, right, across the y-axis at a equals 1. So here for these functions, I have a equals 1. And in this little minor scenario, this graph for C, right, I have a equals 3, making it kind of easy to pick out, right? And so let's chip away at the ones that are obvious first, right? And so if A is 3, right, then this must be the graph for C, or the function for C. All the other ones were not helpful, were not that helpful. What are some other easy wins? You've got two graphs of decay, right? These two are decay, and the others are all growth. So let's deal with the decays first, maybe. Tackle those. So graph A and graph B. We know that in f of x is equal to a times b to the power of x. Right? If b is between 0 and 1, then I have decay. Right? We just established that up here. Right? So I know I'm looking for a graph of with b between 0 and 1 for these decaying functions. So let's see here. These are decay, and that tells me that both of these are graphs of decay. Now we need to figure out A is 1 for both of these, right? And so let's figure out for graph A, I know that f of 1 is 1 times b to the power of 1. F of 1, oh, it's not that easy to tell, is it? Well, we'll have our best guess here. I'm going to zoom in here. What I know about 1/2 versus 1/3, right? 1/2 is larger than 1/3. Yeah? And so kind of I'm going to say that this is at 1/2, making this at 1/3. So for A, B is 1/2, making this part A, whoops, A graph, and this a B graph. By elimination. Now we've got our growth graphs to deal with. We already handled C, and so we're really talking about D, E, and F. They're going to be very similar, but if there is a nice version where it crosses at x equals 1, let's have a look here, right? Because we know for all of these functions, A is 1. And so what I'm looking for is now, okay, if I know that A is 1 and I can figure out a nice coordinate for 1 AB, then that might be nice. I do see two kind of nice looking coordinates here, right? AB is equal to 2, and here AB is equal to 3. The red line, not so much, right? Telling me that's probably e to the x. Huh? So for D, AB is equal to 3, where A is equal to 1, so B must be 3. And the graph for F, let's tackle that. AB is 2, where A is 1 again, so B must be 2. So that means that this must be the graph for F, and this is the graph for D, leaving me with E appropriately for e to the x. Yeah? But notice that it just behaves very similarly to 2 to the x, 3 to the x. It's somewhere in between the two. Right? And it's going to be very similar to 3 to the x. Thanks. Questions? Can transform exponential functions. We're not going to do as much as we did before, where we were stretching and compressing and all that fun stuff, but we are going to flip it and move it around. Yeah? So any transformed exponential, you can rewrite it as ab to the x plus c, where y equals c is the horizontal asymptote. Yeah? And so what that means is that the vertical intercept is then shifted to 0a plus c. Right? And so it can go up or down depending on where the horizontal asymptote is. Yeah? So what we want to do is we want to write an equation for the following graph. Yeah? What I would recommend doing first is figuring out where your horizontal asymptote is. Where is the new step 1? Find the new horizontal asymptote at y equals c. Well, now in this case, right, I see that I have a new horizontal asymptote at y equals -4, which means that c must be -4. I'll zoom in there. It seems to be approaching -4, but never touching it is implied. So just from doing that, I know what my c is. So c must be -4. So in the general form, right, or in the transformed form, I have f of x is ab to the x plus c, but now I just found that c is going to be -4. Or f of x is ab to the x -4. Okay. Next thing I would tackle, probably, is figuring out what the function is at x equals 0. Right? And so in this case, it's relatively obvious to me that it should be equal to -1. And so here, f of x, or f of 0 is -1. So step 2, I'll put it down here, or at least how I would tackle this. Step 2 is find the vertical intersection, or find the vertical intersection f of 0. In our case, we see that f of 0 is -1. We know that the vertical, I knew it sounded weird. It is the intersection, but the word I was desperately searching for is the intercept. Oops. There. That feels better. So the vertical intercept is now going to be at 0 and a plus c. And so we know that at 0, when x is 0, it's at a plus c. I also know what c is from earlier, right? And so here, therefore, I'll say we know, therefore, a plus c is equal to -1. But a plus -4 is equal to -1. So a must be -1 plus 4. So a in this case. Great. Did I do it weird?
Not -5.
Because this is a -4, so then I have to add 4 to both sides. Oh, I'm feeling good about it.
Oh.
I think I just wrote it weird here because I wrote plus -4, but it's really just -4. Technically, all subtraction is just adding a negative. Good. So we're chipping away at this thing. All right. I now have A and I now have C, and so the only thing that's missing is this B. All right. And there's a couple of different ways that you could find B, I guess. But a nice way might be to leverage at x equals 1, because I see when x equals 1, I feel pretty confident saying that the output should be 2. And so here, f of 1 must be 2. So step 3, find a point on the graph you feel confident about. What I mean by that is I wouldn't want you to use, let's see here, -1, right? Even though you might feel comfortable saying -2.5, but you'd want to wait until you've hit a point, and there's really only 2 such points that are showing on this graph, right? Where we can see what the output would be clearly. Okay? And so that's what I mean by feeling confident about it. Okay? So, such as f of 1 is equal to 2. And I guess when I've been oops. Such as, I'll do it in light blue. F of 1 is equal to 2. Which means that ab to the x minus plus c minus plus c. I know a and I know c, so 2 must be equal to a, which is 3, b, which we're finding, x is 1, and c is minus 4. Maybe I will keep this here. F of 1 is equal to 2, and I'll add to solve for b. Well, because now I have 2 must be equal to 3 times b minus 4. So now I can solve for b, and I get 3b is 2 plus 4, which is 6, so b must be 2. Therefore, in general, now that I have a, b, and c, f of x must be equal to 3 times 2 to the power of x minus 4. Nice. Squeezed it onto that page. Any questions about that one? No? Are you ready for some logarithmic functions? Logarithms. Logs, log laws. I love logs. Did I tell you guys when because I did my undergrad in math, and so when I told my grandpa we're talking about it, and he goes, like logarithms and stuff. Ah, yes. I was like, not really, but logarithms used to be really, really difficult to work with, right? We kind of a necessary evil, but for solving things. But yeah, he was like, oh yeah, working on logarithms. I see. I understand. Like, not really. They're pretty easy now on our calculator, right? But we'll see why we needed them in just a moment. Now, logarithms are kind of the inverse of an exponential function. Okay? And so it's how we undo exponential functions. And so logarithmic functions are the inverse of exponential functions. And so they're how we undo exponential functions. Logarithmic functions look like this. And what you'll find is that they have this vertical asymptote. It says horizontal asymptote, but I wrote that down wrong. It's a vertical asymptote. A vertical asymptote at x equals 0, which means that it'll never be able to take a value of x equals 0. And it's going to approach it, but never get there. And so remember how we have those two things that we need to check for our domain, right? I can't divide by 0, and I can't take the even root of a negative number, right? So now what we're going to do is we have to add a third thing to check for our domain. Huh? And so the domain of a logarithmic function, since we can't take the log of x less than or equal to 0, right? So I can't cross this y-axis by any means, unless I've done a shift, but of course we're just talking about the general form. So x must be greater than 0. Huh? And so we add it to our repertoire of checking for the domain. I can't divide by 0, can't take the even root of a negative number, and I can't take the log of 0 or a negative. Right? Usually it's easier to think about I have to take the log of a positive number. Okay, good. So what is a logarithm? A logarithm. Have you worked with logarithms in your other classes yet? You've seen logarithms. Maybe not quite yet, but you will, because a lot of graphs that you're going to make are on a log scale or a semi-log scale, which we'll talk about, right? And so what that means is we've done a transformation by taking the log, right? I think even Allison works on log paper. It's like kind of squished and weird. And so all that's doing is you just avoid taking the log because the paper just does it for you, right? And so, right, I think it's going to be squished, 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 and then kind of more sparse as you move out, right? It is how I would imagine the paper to look. Anyways, so that log paper is just taking the log for you because, like I said, it used to be very difficult. Right now it's not, but we still use it. Okay, so a logarithm, base b, so we can have any base for our log. We can write it as log base b, and so it's here in the little subscript, okay, of x is the inverse of the exponential function base b, which is b to the power of x. Okay. Oops. Let's just talk about these, and then I'll show you kind of how I personally remember these things. And so we're going to have properties of logs that we need to remember. The inverse properties look like this. The log base b of b to the power of x is just going to kind of cancel away, and you're left with x. Notice that these bases are the same, and the power is your x. And so that's because they kind of undo each other. It also means that b to the power of log base b of x, right? Again, the two kind of undo each other, then you're left with x. Right? So it's really a way of simplifying and solving for something when x is in the power usually. Those are the inverse properties, but the one we use the most is the fact that b to the a equals c is equivalent to saying log base b of c is equal to a. And so how I remember this, and I'm going to write this down. Log base b of c is equal to a. What I do first is I take this b to the power of a. That's my first move, right? and I end up with b to the power of a. And then my second move is kind of looping back here, is equal to c. So that's the relationship between the two. Um, So when you see b to the power of a is equal to c, you can rewrite that as a logarithm. Right? And so the logarithm base b of c is just going to be some number. In fact, it's going to be a. So as long as you kind of have this daisy chain under control, then it does take me a little moment to do the reverse, but I know the base of the exponent has to be the same as the base of the log. And I know just kind of going in reverse, so b to the a, if I'm undoing from b to the a to the c, or is equal to c, then I know that it has to be equal to a, and I'm taking the log base b of c. So being comfortable moving one direction allows you to move in the other direction as well. Now, let's do some practice here. What if we have to rewrite these in logarithmic form? Let's see here. Start with a. 2 to the power of 3 is 8. That's true. Of course, all of these will be true. Working from the general form b to the a is equal to c, okay? Now I have log base 2 of 8 is equal to 3. Log base 2 of 8 must be equal to 3. And what I do, because for some reason, I feel more confident moving this way from a log to an exponent, as opposed to moving from an exponent to a log. And so then once I've kind of figured out what I feel good about, then I just check it. 2 to the 3 is equal to 8. Right, and that is where I started. Yeah. Can try it on your calculator, right? Log base 2 of 8, because I know our fancy calculators they have a log, try the log any base of any number button on your calculator. I should have brought the one I snagged. My excellent find. Log base 2 of 8 should equal 3. Right. So our calculators do it now. Right. So, but we need to know the relationship so that we can move back and forth. Did everyone find the log any base button? No. Let me see if I have a picture. You found it? I have my calculator, but that's not gonna help, is it? Don't you have this one on? No? Not on that. Yeah, you have it on that one. This one. This calculator. That's okay. Yeah, this one here. Oops. Ah. Oh gosh. Redo. I'm looking for this kind of button. If you don't have this button, then we'll have a way of dealing with that. Don't you worry. But I do want to just crop this up. I wish I could, maybe I can. I wish I could add this as a sticker. Hey, crop. Wouldn't that be so cute? I'll just add it as a sticker in all my chats. It's a calculator. No, you don't. There, it's all blurry. If you don't have it, it's fine. Yeah. You'll just have to wait another page or so for the solution. But for now, we're just writing them out. Notice that we didn't actually use our calculator to solve the problem, right? We just checked our work. What if we have 5 to the p is equal to q? Okay. And imagine this, not that hard to imagine, you want to solve for p maybe, right? And so how are we going to do that? Well, let's see here. 5 to the p is equal to q. Log base 5 of q is equal to p. Confirm 5 to the p is equal to q. Good. I'm happy with that. Notice that now it's easier to solve for p, right? And so if we're solving for something that's in the exponent, then the easiest way to do that is to take the log or rewrite it in logarithmic form. Notice it is now easier to solve for p. How about the other way? The way I feel more comfortable moving, right, is rewrite these in exponential form. So 3 to the 3 is equal to 27, right? And so I'll kind of jot down those moves here. 3 to the 3, so 3 to the 3. Next move is equal to 27. You can try that on your calculator. Is 3 to the 3 equal to 27? Sure hope so. It is. What about the next one? 4 to the k is equal to n. So second move. What if you want to solve log base 2 of x is equal to 4 by rewriting it in exponential form? So now 2 to the 4 is equal to x. So it looks hard when you see it as log base 2 of x is equal to 4, But if you rewrite it in exponential form, then you have the solution, right? X is 2 to the 4, right? And so therefore, X 2 to the 4, it's been a while, 16. Nice. You have to solve 2 to the x is equal to 12 by rewriting it in logarithmic form. Yeah. And so now, rewriting into a logarithm, I tend to just take a stab at it, remembering that the base of the exponent has to be the base of my log, and so that's a nice place to start. And so the log base 2 of something must be equal to x, right? 2 to the power of x is equal to 12. So you can confirm that you get back to the same thing by going 2 to the x is equal to 12. Log base 2 of 12 is equal to x. This is a number, right? So this is the exact number that is the answer. Okay? So if you don't have a log base anything button, right, that's okay, that is the answer. Okay? Or if you do, or x is approximately, because I'm going to have to round, log base 2 of 12, 3.5849620, using our calculator. If you have, is it in here? It's tiny. Have this, have the button. If you don't, it's okay, right? This is correct. That's the answer. Okay. I'll have to make a note for the test that not everyone has the log base anything button, which is totally fine. I just need to remember that. So, and I'll avoid it. I'll just use common logs or natural logs. First, before we do this, there are two, I can't say common because it's called the common log, but there are two popular bases we use for logarithms. Now, base 10 is called the common log. Usually we don't even write the base 10. So log base 10 is usually written just as a log. As just log. Oh. So when you see something like this, just the log, it's implied that it's log base 10. So log base 10, that's on your calculator, right? Even if you don't have a log base anything button, you have a log button, I guarantee it. There's also going to be the natural log, base E. base E, which is called the natural log. This is one of those things where it depends on what field you're in, okay, what base you're working in commonly, okay? And so for me, in my kind of work and studies in statistics, we tend to only use base E, okay? Which is pretty common. And I have to confirm with Allison if she uses log base E, but I think so. Because a lot of kind of growth things, bacteria, all that kind of fun stuff is working in base E, okay, because it's continuous, okay? Base 10 is more for things like if you're working with sound waves, light waves, all that kind of physics stuff. And if you're in computer science, they work in base 2 usually. Okay? So my default is log base E. Actually doesn't matter which base you use, as we'll see. Yeah. But log base E is written as, now I do this kind of cursive ln because it's my only ln, or because otherwise it looks like one n to me, right? And so when I write my ln, and then I just do a little cursive ln, and that's the natural log. Now, I remember in high school, my teacher would call it the ln. We don't really do that anymore. In fact, I just call it the log. But I understand that that can be confusing because there's only one log for me, and that's the log base E, right? And so we can call it, we call it ln. I don't know how to spell that. Or I usually just call it the log. Because it's my default base. My default base for logs. Like I said, it depends on what field you're in, and what you'll pick up on pretty quickly is what base you should be working in. Yeah. Let's see. I'll move this down here. Page. Which means I didn't need to cram this in here. I'll just, instead of trying to my default base is log base E, or the long, log, I just call it log. Oh. But we can use any base. Huh? Sometimes we pick convenient bases, is what we'll see. Yeah. But my default is log base. Okay. Is there anything else I wanted to say here? I think we're okay. And what you should have, even if you don't have a log base anything button, you should have an LN button, right? And so all calculators, that's what I wanted to say. I knew it. All calculators. I guess I should say all scientific calculators will have a log and LN button. What if we have to calculate these things? Of course, you can use your calculator, right? But I'm gonna add calculate by rewriting in the exponential form. So here, for A, I have log base 10 of 1,000 is equal to, let's call it x. And I want to solve for x, which means that 10 to the power of x must be 1,000. Therefore, 10 to the power of x must be 1,000. Ten to the power of 3. I have to confirm that. Therefore, 10 to the power of 3 is equal to 1,000. So x must be 3. Of course, your calculator can just do it. If you have the log base anything button, you might have to force the log base 10 of 1,000, and you'll find that it's 3. What if you have b, which is log base 10? It's not written, so that implies that it's log base 10 of 1 over 100. I want to find what that is, so I'll set it equal to x. And then I have, okay, so therefore, if I rewrite it in exponential form, then I have 10 to the power of x is equal to 1 over 100, which, if you prefer, you could write it as a decimal. 1 over 100.01. Which is really 1, 2. Move the decimal -2 spots. So then x is 10 to the -2 is 0.01. Try it. 10 to the -2 is 1 over 100. Therefore, or shouldn't do 2, therefore is in the same page. So x must be -2. ln, natural log, that's log base e. So I have the ln of the root of e is equal to x. Rewriting this as an exponential function, I have e to the power of x is the root of e. Right? Going from log base e to the power of x is equal to the root of e. Now, the root of e, remember from the exponent laws that we introduced last week, right? Recall that the root of e, the square root of e, is the same as e to the 1/2. So then e to the power of x must be e to the 1/2. By symmetry, x must be 1/2. Okay. Therefore, I'll say so x must be 1/2. Nice. Good. And these you can check, right? Because all of the scientific calculators have the log base 10 and the log base e button, right? And so if you take the ln of the square root of e, you should get back 1/2. You do. 4.5 if you prefer. Nice. Yeah. This one I find hilarious, but it's a good exercise. We're gonna use your calculator, but not use the calculator to evaluate it in the direct way. So approximate the log base 10 is implied of 700 using your calculator. But not directly. Because you could just do, let's try it. Directly, we find that the log base 10 of 700, because we all have that button, is log base 10 of 700 is 2.8450984, blah, 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 blah. There, we know the answer. But what it wants you to do is say, okay, well, or we can rewrite as an exponential function. Right? Log base 10 of something is equal to 700. And so log base, won't write the 10, is equal to x. So 10 to the x must be equal to 700. Just from how 10 to the x works, right? X, well, if x is 1, let's start there, then I have 10, which is not even close to 700, right? But if I go to 10 to the power of 2, let's see here. Okay, yeah, sorry. I skipped straight to 1,000, but then I tripped myself up. I'll say let x equal 1, right? 10 to the 1 is 10, which is not close to 700. So I let x be 2. 10 to the 2 is 100. Let x be 3, right? I'm getting closer to 700. 10 to the power of 3 is 1,000, which tells me that x must be between 2 and 3. You can do the same thing, right? By maybe saying, okay, if it's between 2 and 3, how about we kind of use the computer science sorting approach, where you just cut it in half, figure out where you want to be, cut it in half again, cut it in half, cut it in half, right? Until you are closest to your approximation, right? And so we consider x equals 2.5, 10 to the 2.5 is something. 316.227766. So we need to bump it up, right? So somewhere between 2.5 and 3, right? But not at 3, because then I've gone too far, right? And so maybe let x be 2.75, halfway between 2.5 and 3. blah, 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 10 to the 2.75. Oops. $562.3413.252. We can keep going. But stop here. We can keep going to find x closest to 10 to the x is equal to 700. But we will say it is between 2.75, x equals 2.75, and x equals 3. And you can keep going smaller and smaller. An exercise in approximation. Now, the meat and potatoes of logs. The most useful log property is that we use logs to solve for values in the exponent, right? And so the most useful thing about logs is that it is the only way to solve for a value in the exponent. In the exponent, right? You have something like f of x is a e r to the x. How are you going to solve for this x? Right? Or f of x is a e to the x. How are you going to solve for this thing in the exponent? Now, that's what the exponent property does for us. But we need, uh-oh, I moved something. I see it. Okay. Exponent. So the exponent property is going to be very, very useful. So I'll highlight it and zoom in. If I take any log, right, of a to the power of r, one of the log laws says that that's equivalent to saying r times the log of a. So what's happened here? And I'm also time, and I can't trust that clock. I should learn. Okay. Doing all right. But if I take the log base b of a to the r, then really what the exponent property says is that I'm allowed to rewrite this with an r in front. That's cool. Because what can I do? If I need to bring something down from the exponent, I just need to wrap it up in a log. Any log will do. Okay. And then I'm allowed to rewrite it as r times the log base b of a. Okay. And so the exponent, right, can be moved down, and now it's just multiplying the log. So here, to move an exponent, can I say down? I don't know how else to explain it. Right? So to move an exponent down, we can wrap it up. We can wrap up the exponential function in a log. And I'll say any base, which is why we have log base b here to indicate that it doesn't matter what base you use. Okay. And that will bring the exponent down, and now it's multiplying the log. And so to move an exponent down from upstairs, all we have to do is wrap it up in a log, any log, and then we can rewrite r times the log base b of a. Where we can easily solve for r. So that's the key. In order to use this trick, though, it's not a trick, it's a log law, which always makes me think of Arrested Development, Bob Loblaw's Lob Blog. You've seen it? Log laws. Bob Loblaw's Lob Blog. Yeah, I think I nailed it. So in order to use this property, or log law, then what we need to do is first isolate the b to the x, right? Or just the thing that's got the exponent on it. And so I'll bump these down here. In order to use this property, though, we first need to isolate the part of the function with the exponential. Part of the function with the exponential, or the exponent, I should say. For example, right, what we want to do is you want to isolate the part of the function with the exponential, which in this case is going to be this part here. Right? 1.3 is all that's to the power of x, right? Which means I need to shake off the 5 before I can use the log law. And so what we find, 5 times 1.3 to the power of x, if that's equal to 10, then the first thing I need to do is isolate the 1.3 to the x by dividing both sides by 5. I get 1.3 to the x is 10 divided by 5, so 1.3 to the x is 2. And I'll just show that that's what I did here. And now it's isolated. Then what we do is we can take the log of both sides, right? Any log base will do. Right? Then, so next, we take the log of any base. I'm going to need another page here. Of both sides. Right? What you do to one side of the equal sign, you have to do to the other side. Okay. And so what we have, and so I will use my go-to ln, right? The natural log, log base e. Okay. So I have 1.3 to the x is equal to 2, kind of picking up from above here. Okay. So now if I take the log of both sides, I have the log of 1.3 to the x is the log of 2. Now the reason I did that is so that I can leverage this property that I can rewrite the log of 1.3 to the x as x times the log of 1.3. So here I get x times the log of 1.3 is equal to the log of 2. Notice the move. Right? But the natural log of 1.3 is just a number, and the natural log of 2 is just a number. Right? And so I can solve for x. X must be the natural log of 2 divided by the natural log of 1.3. This is the exact answer. Sometimes it's nice to get a decimal approximation, right? And so if x is approximately the ln of 2 divided by the ln of 1.3, I get 2.641926.796. The decimal approximation is only helpful if you're trying to solve for t, right? If time is in years, for example, then giving the exact answer is not very helpful, right? Whereas the approximate answer might be more useful. So here, this is the approximate answer. Of course, because you have the choice of using any base, right? This log law will work for any base. So I would encourage you to use a base that you have on your calculator, right? Log base 10, log base e, like we did, right? And so, as I mentioned, right, many calculators only do log base 10 and ln, which is log base e, in which case the change of base formula might be helpful. In which case the change of base formula might be useful. the change of base formula, whoops, looks like this. If I have the log base b of any base of a, that's going to be the same as the log base c. Now I would choose a base c that you have on your calculator, right? Log base 10 or log base e, for example, of a divided by the same log base here of the log base c of b. Okay? So here, pick a base c that is on your calculator. Such as 10 or e. Earlier we found that x was log of 2 over the log of 1.3. That's log base e, right? Log base, let me just 2 over 1.3. Right, so we found the exact answer was the log base e of 2 over the log base e of 1.3. Now what we could do is we could rewrite this, right, as one log instead using the change of base formula, right? And so here, this is the same as, I'll do the log base e just for clarity here of 2 divided by the log base e of 1.3. So here, c is e in this case. A is 2 and B is 1.3. So by the change of base formula, this is going to be equivalent to the log base 1.3 of 2. And so therefore, by the change of base, x is the log base 1.3 of 2. Right? I have the same log base e, right? And b is 1.3 and a is 2. Right? So I can rewrite it as log base b of a. As you become more comfortable with logs in general, I think, what you'll start to do is you might see that, okay, over here, I have 1.3 to the power of x, right? That's my base. So what I might want to do is just take the log base 1.3, right? And then 1.3, the log base 1.3 of 1.3 by a property way earlier. Actually, we don't need to. So when solving 1.3 to the x is equal to 2, let's start there, right? We could have used log base 1.3 of 1.3 to the x is equal to the log base 1.3 of 2. So we could have used the log base 1.3 to match the base in the exponent. Why would we want to do that? Well, let's start by saying, okay, well, I can use the same log property, right? Log law that the x, I can pull it down up front. And so now I have the log of 1.3 of 1.3 is the log of 1.32. Let's focus here. Let's use pink. What if you rewrite this as an exponent? 1.3 to the power of something has to be 1.3. And so here, the log base 1.3 of 1.3 is equal to question mark. There's a reason I didn't use X, because we have, maybe I'll use Y instead of a question mark. Because I've already got an X. But if we rewrite this as an exponent, right, 1.3 to the power of Y is equal to 1.3. Well, then Y must be 1. Right? And so here, 1.3 to the power of Y equals 1.3. Therefore, Y is 1. That's always going to be the case. If you have the log base B of B, it's going to just dissolve to 1. And so this is equal to 1. So sometimes it's easier to just use the same base as you have in the exponent, right? And then it'll just dissolve to 1, right? And so then you have X, oops, I'll use blue again. X times 1 is the log base 1.3 of 2. And then if you don't have a log base anything button, then you would use the change of base formula, right? Log base something that you do have of 2 divided by the log base something that you do have, the same thing, of 1.3. Let me see here. Okay. So now, if you don't have a log base anything button, you would use the change of base formula to solve. Right? Moving kind of backwards. Most of the time, I just tend to use log base E. It doesn't matter because you can always simplify it by using the change of base formula. Okay? And so I rarely, there are, on occasion, I will choose a log base that's the same as the exponent base, right? Just to make it easier, okay? Especially if the exponent base is E, then of course I would want to use log base E, right? Because that, we know, the log base. So notice the ln of e to the x doing the same thing is x times the log base e of something is equal to e. Well, that something must be 1, is x times the ln of e, which is just x times 1, right? So if you take the natural log of e, then you just get 1. So definitely if you have a base e, then you should be using the natural log. Right? Otherwise, it really doesn't matter. You can go log base 10, but it'll be more steps. Okay. We've even got a note here, which got bumped somehow. I know how, but I copied. with our last moments. What if you have to find log base 14 of 3 using only the log or log base e buttons? So remember, log base b of a is the log base c of a divided by the log base c of b. If b is 14 and a is 3, I'll use the natural log, so log base e of 3 divided by the log base e of 14, which is the exact answer. Ln of 3 divided by the ln of 14. I get roughly 0.41628966639. You can try these, but we'll pick up here on Thursday. How about that? If you have any questions, let me know. Otherwise, see you Thursday. I'll stop this.